let's see here about here in this video we're going to talk about interpret driven IO. So there was a problem with programmed IO. What was the problem? The problem with programmed IO is that the processor has to wait a long time for this IO module of this concern to be ready for either reception or transmission of data. That means in programmed IO we know the CPU is completely dependent on this IO device's speed. But IO device is 1000 times slower than CPU, so the CPU has to wait ideally for a long of time, right? So that is the problem which was there in programmed IO. So the problem with programmed IO is that the processor has to wait a long time for the IO module, right? IO module of concern means the device that is needed here for this particular processor for that instruction, let us say. So the problem with the programmed IO is that the processor has to wait a long time for the IO concerned IO module of the concerned to be ready for either reception or for transmission of data. Two things, for either anything doing any IO operation, let us say, the processor has to wait for a long time, right? Because there is a huge speed difference between the CPU and our devices, 1000 times slower it is. So the processor, while waiting, it has to repeatedly interrogate the status of the IO module. It will repeatedly check whether the IO module is ready. Then it will ask, like CPU would ask the IO module, are you ready? Then it will say no. So similarly, it will wait until the IO module status become yes. This repeated checking is known as polling. So this is actually waste for the processor. The CPU is doing no useful work while at that time. It is just repeatedly checking the same status register. So that is why the CPU's time is wasted and the CPU is doing no useful work there. So that is why we can say, as a result, we can say the level of performance the entire system is doing is degraded. The performance is degraded. The CPU is stuck doing what? Polling. So because the CPU is stuck polling, other programs, CPUs just busy there waiting for the status to be yes, right? It is ready to make it is repeatedly waiting there. So what happens because of polling? Other programs cannot run, other IO operations are being delayed, system throughput is dropping. Throughput means the number of instructions which is there in a particular time, that is getting decreased, and the CPU cycles are getting wasted because of this meaningless statistic. So because of this much issues are occurring. What are the different issues because of this is happening is that other programs cannot run, even the throughput is decreasing, and the CPU cycles is getting wasted, and the system's other IO operations are also getting delayed, right? So what are the different problems that is happening here is that other programs execution, they are not able to run, IO operations are getting delayed, throughput is getting decreased, throughput is decreasing, and our CPU cycles is getting wasted. So that is why we have come up with the solution, that is interpret driven solution. An interpret driven solution, an alternative is for the processor to issue an IO command to the module and then goes do some other works. That means the CPU first say, hey IO module, read this data, then the CPU would go and do other works, and the CPU goes off and runs other programs or tasks, and the IO would work independently in the background to do that task that is given in the IO command. This is the core idea of interpret driven IO. So the IO module after finishing the IO operation, it will interpret the processor to request service when it is ready to exchange data with the processor. So that means here when the IO module finishes its work, it sends a special electrical signal that is called as interpret request, that is IRQ, to the CPU through what? Interpret control line on the system bus. So you have to understand here, when the IO module finishes its work, when the data is basically ready, it will send interpret signal, that is IRQ, to whom? To the processor, to the CPU. Okay, and this to the CPU, this interpret request is sent through this interpret control line. and this interpret control line is present in the system bus. Through this, interpret request is given to the CPU through this interpret control line which is present in the system bus. So the IO module will then interpret the processor to request service when it is ready to exchange data with the processor. Right, so now it can request the service. So IO module would send the interpret request signal to the CPU through this interpret control line that is present in the system bus. And now some CPU would say, okay, someone needs me. Now the IO operation has been finished, so I need to go there. So CPU would stop this current task that it is doing temporarily. It will stop and it will go and exchange the data. That is the data which was there in the IO module. Now the CPU can access it, right? So now what happened is that the interpret the processor to now the service. The CPU can give the necessary services to this necessary services. So here it is like this interpret would be like a doorbell. CPU don't need to keep checking the door, right? When there is doorbell rang, then only it has to respond. It doesn't want to keep checking the door to see if someone has arrived or not. Okay. Now the sixth thing is that the processor then executes the data transfer as before and then resumes its former processing. So here later what happened, the processor then execute the data transfer which is there in the IO. Then it would resume where it has stopped. So first, when interpret occurs, the CPU would pause its current task and handle this data transfer, and it returns to exactly what it was doing before after that. So what happened here is that whenever an interpret is happening, the CPU was doing some task there. It will pause that task and then it will go and handle that. Data transfer would happen. Then it will return to exactly where it was after that, right? So this is how it basically works. Now here if you see, there is a diagram here. We have to understand this diagram, okay, which is actually there in our textbook. So here if you see, we have to see how it works from the IO module's point of view. For input, the IO module would first what happened. Let's see how this interpret driven is working in the IO module's point of view. So for the first step, what happened is that the IO module would receive an input. It will receive a read command from the processor. So the sequence begins when the CPU sends a read command to the IO module specifying which device to read from and where to store data. After issuing this command, the CPU leaves and it does not wait there. So this read command would contain which device I have to read from and where I have to store the data. That is there in this read command. The IO module then proceed to the read data in from an associated peripheral. That means IO module now works independently, communicating with its connected physical device and collecting the data. And the CPU is completely free. So here what happened is that the IO module, let's say, it will fetch the data from the hardware and buffering data in the register. Almost ready. That means here what happened is that the IO module now has to work it's now working independently. It will communicate with its connected physical device like keyboard and disk and collects the data. So it will actually communicate with that physical device and it will collect the data from there. It will fetch the data from the hardware or the device which is it require. So here once the data are in the module, so that data will be placed in the buffering data register. When that data has come in the module's data register, the module signals an interpret to the processor over the control line. We told you the interpret is sent to the interpret control line. So when this data has come to this data register which is present in our IO module, we told you the data that is it will the first part happen is that the IO module would work independently and will fetch the data from our physical device and it will keep that data, buffering it in the data register. Now when this data has came in this data register, what happened? it will send the interpret signal to the processor over this interpret control line, right? So in the data register, data is ready. So through the control line, interpret control line, the interpret signals is given to the CPU. Understood? Now the module then waits until its data are requested by the processor. After raising the interpret, the IO module holds the data in its register patiently and doesn't send data until the CPU formally requests it. So it will wait for the request of the CPU to give that data from the data register, right? So the module would then, the IO module then, what it will do is that it will wait until the data which is there in the data register is requested by the processor, because the processor has to come back after, like it was doing something, it has to pause that back and come back when it receives the interpret. So it will hold that data in the data register and it will give it to the CPU only when the CPU requests it. When the request is made, the module places its data on the database and it is then ready for another IO operation. So now it receives the request from the CPU, then it will take this data and put that in the database, which is the system, in the system bus it will put in the database. Then now this module is ready for doing the next IO operation. This is how it works in the IO module's point of view. It receives this read command which contains which device it has to read the data from, and it also contains the location in which it has to be stored, where you have to store the data. The IO module would now communicate with this connected physical device and fetch the data, and it is going to buffer it and store it in the data register. So now the data is in the data register. Once the data has came in this IO module's data register, it will then send what? The module signals. To whom? It will then send the interpret signals to the processor through this interpret control line which is there. So now what happened is that the module would keep the data in the data register until the processor is requesting for it. When the processor requests it, it will send the data to the processor through the data bus. Understood? This is what is happening in the IO module's point of view. Now let us see what is happening in the processor's point of view in the interpret system. The processor is sending a read command, then it then goes off and does something else. That is, CPU first sends the read command to the IO module, then CPU immediately switches to the other task. It runs program A, program B, lot of things it will do there, right? The CPU is now getting productive. It is not sitting there idly, right? Instead of sitting idly, it is now becoming productive, and it then goes off and does something else after sending the command. At the end of each instruction cycle, the processor checks for the interpret. The CPU follows this cycle for every instruction. See, while it can do a lot of instruction by that time, it can execute lot of instruction by that time. You know what instruction cycle? We know fetch instruction from decode the instruction, execute the instruction. After executing these instructions, it checks for pending interprets. Okay, if there is no pending interpret, then it will go again for fetching another instruction. If there is interpret, then it will handle it. This is what is happening. This text happens automatically at the hardware level after every instruction. That means here in the processor's point of view, we know instruction cycle. It first fetches one instruction, it would decode that instruction and execute that instruction. After finishing executing one instruction, it will check if there is any interpret, if it has to handle something. If it has to handle, then it will handle that. Otherwise, it will go on and fetching another instruction from the memory, decoding that and executing that. It will continue doing that. So the processor would check for the interpret at the end of each cycle. Now you have to understand, when the interpret from the IO module occurs, the processor saves the context. That means the processor would save its program counter and processor register of the current program and process the interpret. That means when interpret occur, what is the things that the processor is saving? It will save the program counter. Remembers word to return after interpret, right? So it will save the program counter, CPU register. It will preserve all the calculation value, that is CPU's register, and also status of flag, preserves the condition code, flag, status and all, and stack pointer, maintains memory stack position. These are the things that it will save. Then after saving this only, it will go and handle the interpret and process the interpret. So when an interpret occur, what happens is that the IO module, when an interpret is coming from the IO module, the processor would save its program counter, its registers, CPU registers, its flag register and flag or status register to know its condition, okay, to preserve the condition, and also stack pointer. These four things you have to understand what it saves. So in that case, what happened is that the what happens is that the when an interpret is received from the IO module, the processor would save the program counter, CPU registers, flag registers, and the stack pointer. Understood? These much thing it will basically save. This saved context is typically stored on the stack in the memory. This saved context where it is stored. So since I am maintaining a stack pointer, these saved things will be stored on the stack in the memory. So let's say program is running at one address, interpret occur, it will save the CPU, R1, R2 flags, all these things, and then CPU will jump to the interpret service routine. Interpret service routine is where we are handling, that is called as handling the interpret, is known as the interpret service routine. Understood? So here this is what is happening in the processor's point of view. So it will, all these saved things are stored in the stack, okay, stored in the stack. Then after saving only, it will jump to what? Interpret service routine. Understood? So in this case, the processor reads the word of data from the IO module. It will take the data from the IO module and then stores it in the memory. That is the final thing it does, right? CPU execute the interpret service routine, a special piece of code that reads the data. That is, it's a code. Interpret service routine is a code that reads the data from the IO module's data register and transfer it to appropriate memory location and acknowledges the interpret. So acknowledges the interpret means, so the IO module will know it is done. So here it is happening. Interpret service routine means first it will read the data from the IO modules. In AL we know it is reading the data from the IO module's data register. Then memory instruction, we will write it like this. That means we have to write the data to the one memory location. I have to write the data. So I am storing that data in the memory. So I will write this instruction. Okay, this is how the interpret is handled. Then I will give, here interpret handling is completed. Now I will give and acknowledge this interpret, so that why I am doing acknowledging the interpret, because then only, not me, CPU is doing, okay. So then only the IO module would know that this is done. Finally the data has reached the memory, it is done. So you have to understand that it will read the data from the IO module and then it is going to store it in the memory. So for that the CPU would execute some interpret service routine. In interpret service routine, it will read the data from the our IO's data register and move it, that is MOV, move it, writing it to the one memory address will be the to the memory, and finally acknowledging the interpret, so the IO module will know that it has been done. It then restores the context of the program that it was working on, resumes execution. That means here it will restore the saved program counter, registers and flag and all. Then it will resume doing what it has stopped before because of the interpret. Okay, so let's compare the efficiency in programmed IO and my interpret driven IO. Let's see here. Here in programmed IO, issues a command, wait, then transfer, then resume. So here this much time it has to wait. Here issue command, then program A, program E and all is occurring. Then through interpret service routine it will transfer and then resume, doing other things, right? So here this much time it is waiting, right? But here other instructions can be executed in this time. So more efficient is what? Interpret IO, right? Because CPU is more productive in interpret driven IO. Now however, there is a problem in interpret IO, that is it still consumes a lot of processor time. Because why? every word of data that goes from the memory to the IO module or from the IO module memory must pass to the processor. That means if I wanted to, like here, if you see the data path and interpret, IO module, from the IO module CPU read it and then CPU has to write it to the memory. So if I want to write anything from the IO module to the memory or from the memory to the IO module, it has to go to the CPU. So that means we have to transfer a large file and the CPU must handle each word individually through interprets. So that means if I wanted to transfer a large file from the IO module, CPU must have to, every single word it has to transfer through interpret, it has to transfer. So this can also waste CPU's lot of time on data moment. That is, on data moment, a CPU's lot of time would get wasted because every single word of data has to be transferred from the IO module to the memory. Individually we have to, CPU must handle each word, right? So CPU is handling each word individually through this interpret. So what happens is that CPU's lot of time is getting wasted because of this. So because in our data path there is CPU in between, you can see here, right? CPU is in between. So you can see here CPU is actually there in between. So that means this is wasting a lot of CPU's time. So transferring a large file, what happens is that CPU must handle each word individually through interpret. This still wastes CPU's significant CPU time is wasted here. So to solve this, we are having another technique, that is the direct memory access, DMA. So DMA comes to solve this issue. So we will understand what is DMA in detail later. But to solve the problem here, which is there in interpret IO, we are using DMA. Okay. So now next is about this diagram. Next is about this diagram, which we will be learning in the next video because it has been a pretty lengthy video. Thank you.